Alright, so let's take a look at part 2. We're going to do the graphing and the free response problems. So for the graphing problems, first, if you have a linear function, which is clearly linear because you have x and y there, you don't have x squared, so it's not quadratic, it might be easier to do, you can do it two different ways. You could find the x and y intercepts and graph it, or you can find the slope and y-intercept and graph it. One way to do it is to solve for y pretty much. So you can subtract 2x from both sides. We are not dividing, that was just underlining that. Okay, start by doing that and say 3y equals 12 minus 2x, divide by 3. You get y equals 12 minus 2x all over 3, which can be written as y equals 12 over 3 minus 2 over 3x, which finally can be written as 4 minus 2/3 x. Now, it doesn't look like that's in slope-intercept form, but it actually is because we have negative 2/3 x plus 4. So that's one way to do it, okay? And again, remember, this is your slope, this is your y-intercept, okay? Think about this for multiple choice too, if you have to match your graph, and to make sure you know that the slope and the y-intercept, what each of those are. So that's one way to graph this problem. Another way to do it is to find the intercepts. So to find the x-intercept, let's set y to 0. So again, we got 2x plus 3y equals 12. So to get the x-intercept, I'm going to just drop off the y part. I'm going to say set y equal to 0, and I get x equals 6. If I want to find the y-intercept, I take that same original function up here, and now I set x equal to 0. I'll have 3y equals 12, and that'll tell me y equals 4. So those are my two intercepts. I can graph it that way, or I can graph it with slope-intercept. But it doesn't matter either way. And notice, your y-intercept from slope-intercept form is the same value, whether you do it with roots or whether you do it with slope-intercept. Now I know that my intercepts are going to be 6 and 4, respectively, for x and y. So if I want to graph this, let's say I'm going to graph my y and x axis here. Okay, I label my axes. I also label my increments. If my x is going up to 6, I might want to go by 2's on the x-axis. My y's are only going up to 4, so I can go by 1's there at least. Okay. So I've got an x-intercept at positive 6, which is right here. A y-intercept at 4. 1, 2, 3, 4. There's the 4. And simply connect. And take a look. If you did this the other way, you get the same answer. Start at the y-intercept of 4. Look at your slope. Your slope says negative 2/3. Okay? So I've got to go down 2 in the y. So down 1, that brings me to 3. Down 2, down to the 2. Then I got to go over 3 to the right. Well, over 3 to the right is really over 1, 2, 3. So there would be my other point right there. It's a little bit off, obviously, because we're sketching, but it would still be the exact same graph. Okay, and remember, this is a complicated one because my scales are different. So if I'm looking at this again, I go down 2. That's my delta y, negative 2, right here. And then I get to the right 3. Well, to the right 3 is just 1.5 boxes, because 3 to the right would be these 2 boxes plus another half of a box. Okay, so I'm looking at 1.5 boxes. That's where this point comes from right here. Okay, that's where that point comes from right there. That's your way to graph linear functions. Let's look at quadratics. For quadratics, depending on what form it's in, if it's in vertex form, it's pretty simple actually. This example happens to be in standard form. So in standard form, we start with our axis symmetry, x equals negative b over 2a. Okay, we're going to get negative 16 all over 2 times 4, which is negative 16 over 8, or simply negative 2. That's my axis of symmetry. So already I know that my axis symmetry is about negative 2. If I want the vertex, I take that negative 2 and plug it back in. So to find the vertex, or the y-coordinate, we say 4 times negative 2 squared plus 16 times negative 2 minus 9. Again, I'm taking this negative 2 and plugging it in to get the vertex. This will be 4 times 4 plus, oops, let's use an eraser because we have one, minus 32 minus 9. 4 by 4 is 16, minus 32 minus 9. That's going to give us negative 25. So my vertex, that's my axis is right here, and my vertex is negative 2 comma negative 25. Okay, again, the problem doesn't really matter what it looks like. All that matters is that we know how to do the steps. So we got the axis and we got the vertex. For the roots, personally, I would just plug it in my calculator to find the roots in our program we wrote. But if we use our quadratic formula here, which I'm going to leave you to do, using the quadratic formula for the roots, you're going to get negative 4.5 and 0.5. So right away I have to think to myself, my vertex is down at negative 25. So my y-axis is going to really extend downward. So I'm going to go like this now. I'm going to do that. And then I'm going to shift my graph over a little bit because I know that the axis symmetry is going to be at negative 2. Okay, so let's see, I'm going to put my roots first. That 0.5 is right here. Negative 1, 2, 3, 4, 0.5. Again, I'm going by ones here on the x-axis. Okay. The axis of symmetry goes through negative 2. That's right here. But now I need a vertex down at negative 25. Negative 25 is my y-coordinate of the vertex. So I might have to go by increments of 5 here. Okay. So let's just say 10, 20, 30. Again, all negative quantities. Negative 10, negative 20, negative 30. Here's negative 2, negative 25. There's your vertex, and there's your graph. Why does it open upward? It opens upward because A is positive. Why are there 2 roots and they're on the axis? Because the discriminant is positive here. Okay? So we have a reflection about the line also, x equals negative 2, which is our axis of symmetry. The third one. Here we have x cubed minus 4x squared minus 11x plus 30. Clearly here we have a polynomial function. First, y-intercept. Always set x equal to 0. So these would all drop off. Here's your y-intercept. So we start with the coordinate 0, 30. That's our y-intercept. Next, if I want to find the roots, I have to think about my synthetic table. Use my synthetic chart. So if I use my synthetic table now, I'm going to put my coefficients up top. 1, negative 4, negative 11, and 30. Let's start with 1. Bring down the 1. 1 by 1 is 1, minus 4 is negative 3. Negative 3 minus 11 is negative 14. Negative 14 plus 30 is going to be positive 16. So I still don't have a root yet. Let's try 2. Bring down the 1. 2 times 1 is 2. 2 minus 4 is negative 2. It's going to be negative 4 minus 11 is negative 15. Negative 30 and 30 is 0. So this is a root. Okay, so already I know that one of my roots, and I'm going to list my roots on the side, is going to be 2. Now I can just bring down these values and write my resulting polynomial, or my resulting quadratic, whichever you'd like to call it. This one's pretty easy to factor. Then we're going to get, let's see, x minus 5, x plus 3. So this factors into x minus 5, x plus 3. Okay, remember when we're finding the roots, we're setting the y equal to 0, really. So this is really equal to 0. If I make a t-chart, x minus 5 could equal 0, x plus 3 could equal 0, so x is negative 3, and x is positive 5. So 5 and negative 3. And it would work if you tried them in the synthetic table also. So I've got my 3 roots. How do I know there are 3 roots? Well, I take a look at the original and I see that it was x to the 3rd. So there must be 3 roots. There must be. 2 of them could be imaginary, but there must be 3 roots. So we've got our y-intercept here, and we've got our roots right here. Okay, y-intercept and our roots right there. Next, if we want some intermediate points, okay, we want some intermediate points that might help us out, or some end behavior to help us out. Let's take a look. We've got an odd exponent, or an odd degree, and a positive 1 as a leading coefficient. When it's odd and positive, I think of a linear function going up like that. Because again, odd is like a linear function, even though it's cubic. It's like a linear. And when it's positive, I think of a positive slope. So I know that my graph, no matter what it looks like, is going to be, again, something where the ends go off like that. Okay, the ends go off like that. Now I'm going to have a root at negative 3 there. I'm going to have a root at positive 5 and a root at positive 2. So I can already see the general shape that I'm going to get from this graph, where my y-intercept is around 30. But it helps to have some intermediate points also. Okay, so let's go ahead and graph this now. I know I'm going up to positive 30 on the y-axis, so I might want to consider that when I'm going my increments here. So let's go by 5s on the y-axis. Okay, along the x-axis, excuse me. Along the x-axis, let's just go by 1s because my roots only range from negative 3 to 5. Okay, so I'm going to go by 1s along the x-axis. So I start by plotting my roots. I got a root at 2, I got a root at 5, and a root at negative 3. We've got a y-intercept at 30, 5, 10, 15, 20, 25. Up here is 30 up here, so I'll put it all the way up there. We know the end behavior is down on the left, up on the right, because it's an odd function with a positive leading coefficient. And now I just need some loops here. So if I want to think about a point in between these roots here, well, what's between 2 and 5? I might pick a number like 3. If I plug a 3 into my function, I'm going to get negative 12 as coordinate. So here's 3 right here. 1, 2, 3, okay? When I go down to negative 12, well, that's about right here. So I can tell that that loop is going to go that far down. Then I know along my y-axis here, it's going to hit the y-intercept, but then it might go up a little further. So I'm going to pick another point. And if I plug in negative 1, I'm going to get 36 as my coordinate. So 36 is a little bit higher. It's even further up here. So I know that this will loop up, and then come back around. Again, it helps to look at this on the calculator if you like. So when you're graphing these, use your calculator to assist you, but make sure you show all your work. If it's a problem like a multiple choice and you can just look on the calculator, you are more than welcome to just look on the calculator. I can't stop you there. Last one, we have a square root function. I know that the square root here is going to look something like this because it's positive. Okay, I know I'm going to have some sort of a shift, but if I pick my points properly, I can make my xy table. Remembering that I want to get a quantity under the radicand, or under the radical, which is called the radicand, that is a perfect square. So if I start with -2, I'm going to get -2 plus 2 is going to be a 0 there. Then I start with my -1, because -1 plus 2 is going to give me +1. Then I can go ahead and put a 2 in. I can put a, let's see, a 2 will give me a 4 into there, a 7 will give me the 9, and a 14 will give me the 16. So I know that the y value, if I plug in a -2 up here, plug in the -2, you're going to get this to be 0, times 2 is still 0, minus 3 is -3. And then remember that a value in the front indicates whatever the shift is, or whatever not shift, the increment along the y's for these setups. So we have -1, 1, 3, 5. Again, noticing these are all going up by 2's. Okay, every time it goes up by 2. Again, the other way to think about this is you have a shift. You have a vertical shift of -3 down, a horizontal shift of left 2. That's where the first vertex, or the first coordinate, which is the vertex, comes into play. So we got an xy axis here. We're going to go down 3 over 2. There's my vertex. I'm going to eventually go up, so I have -2, -3, -1, -1, 2, 1. Then I've got 7. Whoops, 7 is going to be all the way out here. 3, 4, 5, 6, 7. 7 is going with 3. That's going to be up here. You can see our general shape. Okay? Again, this is your vertex, your starting point, which happens to be the same thing as the opposite of h and the same as k. And notice these all go up by 2. They go up by 2 each time. Again, you can graph this in your calculator and take a look as well. Number 31, solve the system of equations algebraically. So systems of linear equations. You can check with a matrix if you would like, that's fine, but you need to solve these algebraically. The first thing I notice is that I can use substitution or elimination. I would personally use elimination because I see here that they're already lined up. So if I simply multiply the top equation by 4, I'll end up with a -4y. So I get 2x, oops, not 2x, gotta multiply by 4. 8x minus 4y equal 12, and x plus 4y equals 6 still. So again, what am I doing here? My operation is 4 times equation 1 plus equation 2. Okay, think back to your notes, we did this. So 4 by equation 1 plus equation 2. Adding down now, take a look. You end up with 18 equals, these drop off, they cancel. You're going to get 9x, thus x equals 2. Well, if x equals 2, I can take that and plug it in either equation. I would probably plug it in here. Or here, actually. It doesn't matter, either one. So I'm going to plug in the second one, let's say. So I got 2 plus 4y equals 6. Subtract 2 from both sides, you get 4y equals 4, thus y equals 1. So my answer as a coordinate is 2, 1. How do I check this? I can check it by hand by plugging them both back in or do a matrix. My matrix will look like this. Okay? And when you do RREF, row reduced echelon form, you end up with 1, 0, 0, 1. You'll end up with a 2 here and a 1 right here. Okay? How do you do that again real quick? We got, let's see, 2, -1, 3. Let's do this. Second matrix. I'll go over to edit. This is a, oops, 2 by 3, my bad, 2 by 3 matrix. Let's see where we're at. We got 2, -1, 3, 2, -1, 3. And then we've got, whoops, where are we at? 1, 4, 6. 1, enter, 4, enter, 6, enter. Second quit. Clear out whatever's there just to be safe. Second matrix, over to math. RF, I'm going to press up to get there quicker. And the letter B is there. RF of matrix A, second matrix of matrix A. Close, close. Oh no. Let's go to our syntax error. I closed it twice by accident. There it is. And again, this tells us, really, x plus 0y equals 2. That's the first line that we get there. The second line tells us 0 plus 1y equals 1. There's a 1 in front of this x, really, sorry. Just in case you guys didn't see that. There's really a 1 in front of the x. Well, 1x equals 2 is the important part. This doesn't matter. Same thing here. This doesn't matter either. So this really tells us that x equals 2 from this part. and y equals 1 from this part, just as we had gotten a minute ago. All right. Number 32, part A. Find the inverse of the following function. All right, so let's do this quick. Inverse. You write it as y equals x squared plus 2. Switch x and y, because the inverse is defined as switching x and y. And then resolve for y. So move the 2 over. You're going to get x minus 2 equals y squared. Bring it up, take the square root. You're going to get plus or minus the square root of x minus 2 equals y. And I write it, as you remember, as f inverse of x. Okay? That's my inverse function. Part 2, or part B, says prove after that it is correct by checking the composition of f and f inverse and getting x. Well, that's what we proved. So I think we only did this in the honors section. So this section, this might be a little bit new, but it's not going to be, it won't be a topic that will be assessed for the non-honors section. For this problem, I can take a composition and take my inverse and plug it into my original. So if I'm doing my inverse in the original, it means to take the inverse function and simply plug it into the original where you see an x. So we end up with plus or minus root x minus 2, that whole thing squared, because that's all going in for x there, and this squared is still there, plus 2. Well, a square and a square root actually cancel, so you're left with x minus 2 plus 2, which is really just x. And remember, when you do a composition of two functions, if you get x out, it means that those functions are inverses of one another. All right, the final problem. The final problem, Mr. Smith is cooking baked ziti for lunch without any meatballs, Mr. Smith. He bakes the ziti completely, and it is a temperature of 90 degrees Celsius, so a starting temperature, we can think of the starting temperature. The temperature in the room is about 35 degrees Celsius, and he wants the actual temperature of the food to cool to about 45 degrees Celsius. The cooling rate of pasta is 0.06. Find how long it will be before he can eat the lunch. All right, so let's start by listing. The initial temperature of the pasta is 90 degrees Celsius. We know that right away. All right, that's good. Let's see, the temperature in the room is 35 degrees Celsius. He wants the temperature, the actual temperature, T, to be 45, and we know that the rate of cooling is 0.06. So let's go ahead and plug in our formula now. So we got 45 equals 90 minus 35, e to the negative 0.06 T plus 35. This is called Newton's law of cooling. You will use this many, many times in any science and engineering background. You can also show where this law comes from in calculus, and you'll be able to do that when you take calculus. So here we have 45. What I'm going to do first, actually, is combine these two. The 90 minus 35 that you see there, let's combine those two and write those. So we're going to have just 55 e to the negative 0.06 t, while at the same time, let's subtract 35 from both sides, okay, yielding a 10 over here. So this is what we have now as our equation. Well, I got to get rid of that 55 before I can solve this. So divide by 55, I get 10 over 55 equals e to the negative 0.06 t. But 10 over 55 is really 2/11 equals e to the negative 0.06 t. All right, now with that said, I can then think about this problem and do one of two things. I can solve it by hand using logarithms by converting, or I can use a graphing calculator and look for the intersection of the curves. So I can graph this in y1 and graph this in y2 and look for the intersection. That's one way to do it. Or just convert to logs. Let's convert this back to logs. I remember that the base remains the base, so it's going to be a log base e, because e was the base, so it's still the base. And e, remember, is a number, approximately 2.71. So the base remains the base. The argument, okay, comes from the other side, and we know that it is going to be negative 0.06 t. Now, log base e, log base e, log base e, it just means natural log. So in your calculator, you can use ln of 2 over 11 equals negative 0.06 t. Well, we need to know what ln of 2 over 11 is, right? We have to know what the actual value is. So let's go ahead and figure that out. So let's do the natural log. Let's clear this out. ln, again, ln is right over here. I'm not highlighting right here. ln of 2 over 11. Okay, that's what my answer turns out to be. Now, again, I'm gonna round probably right now. So negative 1.7 approximately. So let's go back to our problem here. Okay, so we've got really negative 1.7 equals negative 0.06 t. So divide by negative 0.06, divide by negative 0.06. And go back to your calculator and don't erase what you have there. Just hit divide by negative 0.06, so it stores all those decimals. and you'll get 28.41. And let's go back to our problem. Where is it? Whoops. There it is. Okay, and what did I just say? I said 28.41. 28.41. And in this case, we are in minutes. Okay, in minutes. All right, and this should be with units of minutes there. So the problem takes about 30 minutes before Mr. Smith can actually eat his pasta. Is that realistic? Obviously not. Hopefully it's like maybe, what, 3 minutes before you can eat your pasta? So in this problem, maybe we should have made it in seconds. You know, after 30 seconds, it'll be cool enough for him to eat. Anyway, that's it for the review packet for your sample. Remember, people, these are just sample questions. Just sample questions. There are many, many other possible questions that can be asked on your exam, so make sure you study all of your concepts.